The solar system is on edge tonight. Comet 3I/Atlas, the third verified interstellar guest, will skim by Mars at a mere 0.19 astronomical units, with all the planet's satellites scrambling to uncover its mysteries. Yet this encounter goes beyond a routine pass. The visitor's vivid green halo, unpredictable tiny boosts in speed, and chemistry dominated by carbon dioxide have already upended the standard comet guidelines. Telescopes on Earth are on the verge of losing sight, relying solely on a few Martian spacecraft to bridge the gap to reality. Could 3I/Atlas be an eccentric comet, or perhaps a crafted entity redefining what we mean by extraterrestrial? With the timer reaching 0, signs of breakup, irregular throbs, and bizarre spectral features might transform our understanding of cosmic intruders. Will the coming hours expose the phenomenal, or confirm that science retains the ultimate say? Just 6 hours remain. The brief period before Earth's line of sight to 3I/Atlas slips away behind the Sun. At 0.19 astronomical units from Mars, roughly 28 million kilometers, the interstellar wanderer hurtles by the rusty world right as terrestrial gear falls silent. This darkness stems not from equipment issues or oversight, but from orbital alignment. For a short while, Mars serves as the sole observatory in the solar system. Key orbiters like MAVEN, Mars Express, and ExoMars TGO ramp up to intense monitoring, their operators executing pre-planned routines while adapting in real time. In MAVEN's operations hub, the Red Watch team steps up front and center. These specialists, prepared for crises, navigate decision trees for any unexpected developments. Prior to the signal loss, they practice quick toggles from routine observations to high-speed spectral scans, primed to adjust if an abrupt burst or fragment warning appears on monitors. Reserve setups are in place. Verifications occur with TGO and Mars Express personnel. All instructions get recorded. Each data stream receives a duplicate backup. There's zero tolerance for breakdowns when the wider solar system can't see. The timeline allows no slack. Mars Express captures wide-field photos at short intervals, layering shots to detect the slightest evidence of splitting or trajectory shifts. TGO's analyzers probe the halo for unfamiliar wavelength patterns. MAVEN's detectors for particles and magnetic fields track atmospheric waves, seeking traces of artificial influences. The energy and communication limits of each probe are pushed to extremes, with viewing times bargained to the second. Should a debris cloud pose a risk, Mars Express can shift to protective monitoring, foregoing readings to ensure safety. The cutoff point for evasion is set 30% beyond the previous peak in density. The Earth's communication void represents more than a mere link failure. It's a trial for the whole field of planetary exploration. The Red Watch Coalition functions as the central hub, passing orders and info via slim transmission slots, emphasizing equipment welfare and syncing with rovers like Perseverance and Juron. In the command centers, timers tick alongside the object's inbound path. Beyond those walls, hobbyist networks scan for initial photometrically anomalous jumps, set to feed info into the worldwide warning system. During these 6 hours, the outcome of the vigil and the verdict on whether 3I/Atlas marks a stellar quirk or a deliberate creation hinges on the prowess of these few satellites and their crews. The pressure mounts genuinely. The leeway for mistakes is paper-thin. As the opportunity tightens, each moment turns into a possible game-changer. A series of puzzling emissions has trailed 3I/Atlas from its initial spotting. The first clues emerged from a home observatory in Pune, India, where citizen scientist Priya Rallo observed a recurring flicker in the brightness pattern, intensifying and dimming to a beat that no comet manual could justify. Her report sparked interest, yet the peculiarities grew as expert facilities tuned in. Photometric logs reveal the body's luminosity spiking at 2 consistent intervals for sporadic gas releases. The throbs occur with almost exact separations, bucking the irregular, isolated bursts common in ordinary comets. Every peak hits with a precise start and smooth fade-out, resembling activation and deactivation by an invisible force. Even nearing the Sun, the rhythm stayed steady, unaffected by range or sunlight interference. Spectral analysis delivered another shock. Rather than the expected water vapor signatures, carbon dioxide emerged as the primary marker in all readings. The CO2 to water proportion exceeded 8:1, far surpassing even the gassiest known comets by a factor of 10. This composition is so uncommon that simulations in labs fail to replicate it fully. Accompanying the CO2, the halo shines a steady emerald, cresting at 516 nanometers. This hue endures across devices, validated by both terrestrial and spaceborne instruments. Typical culprits like C2 swan bands, carbon monoxide, and other emissions fail to explain the strength or the consistency of it. The greenish tint in the comet's coma stands out, dominated by nickel emissions at 337 and 380 nanometers that overwhelm iron lines by factors exceeding 4, flipping the pattern observed in all documented comets from our solar system. Observations through imaging and polarimetry reveal further peculiarities. The coma's verdant hue pairs with a pronounced negative polarization curve, a feature more typical of rocky asteroids than frozen vagabonds. The dust tail displays particles that are bigger and less speedy than usual comet debris, following paths that defy straightforward simulations. These particles follow a wide, sluggish curve, as though ejected via a process that dispenses material in controlled spurts rather than erratic sprays. Astrometric measurements, on the other hand, detect subtle accelerations, minute adjustments that fail to match any familiar outgassing patterns. Each slight shift aligns with a flare in brightness, implying a connection between luminosity and movement. No individual oddity exists in isolation. Collectively, they paint a picture of an entity that defies conventional classifications. Photometry, spectroscopy, and astrometry all contribute to an expanding collection of enigmas. The data accumulates, awaiting a unified theory that accounts for every detail. Planetary experts initially relied on fundamental principles of physics and chemistry. For primary theories, each rooted in proven frameworks, have been evaluated against the mounting peculiarities of 3I/Atlas. One proposes a composition forged in extreme chill. According to this idea, 3I/Atlas originated in regions distant from any sun, where water solidifies and exotic ices like carbon dioxide, carbon monoxide, and others prevail. Comets from the Oort cloud suggest such origins, yet none exhibit a carbon dioxide to water ratio as skewed as 8:1. Nevertheless, proponents argue that the expanse of interstellar space is immense, and our sample size is minuscule. One exceptional case might redefine comet chemistry. Another approach emphasizes internal architecture. Buried volatile chambers, holding compressed gases, could burst forth as solar heat penetrates the surface. If these chambers are unevenly placed, they might account for the periodic brightness variations. Experiments in labs demonstrate that minor thermal gradients can ignite abrupt ejections, potentially recurring in layered structures. While consistency is uncommon, it's feasible in an object sculpted by eons of space erosion. A third perspective involves dust behavior. The coma's jade shimmer and the abundance of hefty, sluggish grains may stem from atypical dust makeup or grain sizes. Interactions with the solar wind and Mars's feeble magnetic field could sculpt the tail, guiding ionized particles into expansive loops. Simulations of comet tails indicate that, under specific configurations, denser grains trail slowly, forming relaxed bends that resemble the detected ejections. The asteroid-like negative polarization might indicate dense, carbon-laden particles instead of fluffy ice. Lastly, certain experts question the adequacy of current simulations. With just 2 prior interstellar intruders cataloged, each newcomer challenges the limits of our computational models. Those tiny accelerations and aligned pulses could arise from dynamics our programs haven't yet incorporated, like nuanced interplay among radiation, gas venting, and rotational wobbles. Here, the irregularities signal not design, but the vast unknowns in natural processes. For every conundrum, researchers insist on ruling out all conventional causes before entertaining unconventional ones. During these 6 hours, Mars serves as the solar system's sole vantage point. 3 spacecraft, MAVEN, Mars Express, and ExoMars Trace Gas Orbiter, anchor the observational network. Each deploys unique tools, designed to detect varied aspects of 3I/Atlas's flyby. Maven's ultraviolet spectrograph, optimized for dim signals, scans for faint UV signatures in the tail, particularly indicators of breakup or sudden flares. Its detectors for particles and magnetic fields, operating at peak speed, monitor for disturbances in Mars's ionosphere. A surge in ions or a field distortion might indicate influences beyond ordinary reactions. Should the comet's dust or ionized gas engage the atmosphere, Maven's instruments would detect the impact first. Mars Express employs its visible imager and infrared spectrometer for straightforward visuals. Layered wide-field shots follow the coma's evolution, seeking clues of fragmentation or morphological shifts. The spectrometer, covering UV to IR wavelengths, hunts anomalous spectral features, unforeseen emissions, or depleted water signals. Its Aspera 3 plasma instrument tracks high-energy ions that might reveal atypical exchanges between the comet and Martian surroundings. ExoMars TGO's NOMAD and ACS units examine the coma for minor gases, targeting odd isotopic mixes or molecular markers alien to solar system bodies. The KSS's high-res imager strives to capture split-offs or active dust streams as they unfold. Each instrument readings are recorded with precise timestamps, cross-referenced instantly across various teams. At ground level, the Perseverance and Juron rovers detect subtle indicators like atypical dust deposits, shifts in the atmosphere, or faint auroras along the skyline. Their onboard sensors and imaging systems offer supplementary proof, albeit with reduced precision compared to the orbiting observatories overhead. The protocol outlines clear criteria: patterns of breakup, alterations in path following a burst, unexplained spectral signatures or radiation profiles, isotopic compositions deviating from solar norms, and evidence of artificial timing in signals or velocity shifts. Any irregularity noted by one device requires validation from at least one other. Isolated observations fall short. Solely when data from diverse sources and viewpoints align does it shift from mere curiosity to groundbreaking territory. All incoming Mars data undergoes rigorous scrutiny before integration into official records. Initial validation emphasizes duplication. Signals from satellites are copied, timestamped, and archived by separate Earth-based facilities spanning the Atlantic. This setup protects against solar disruptions, signal glitches, and occasional data degradation during communication gaps. Delays in telemetry, which can extend to hours due to routing via relay SATs and distant receivers, introduce further variability. Control groups fast-track packets highlighting potential breakups, unusual spectra, or sudden path deviations, subjecting them to swift multi-check processes. No lone detector or crew can approve a warning independently. Each potential incident demands review from a minimum of 2 systems, with unprocessed feeds shared in public repositories once transmission capacity permits. Tracking procedures go further than mere figures. When an orbiter's sampler captures a dust particle or ice shard, contamination control experts intervene. These officers apply rigorous containment measures. Specimens get enclosed, labeled with codes, and documented using cryptographic seals that need approvals from both NASA and JAXA prior to examination. The aim is unambiguous origin tracing. Any biological traces in Martian soil or air post-encounter must link back clearly to the interstellar object or to the planet itself. Subsequent searches for life rely on distinguishing arrivals from 3I/Atlas from native elements. Even ancillary details like timestamps, positions, and device calibrations are stored in secure, unalterable logs, allowing audits long into the future. Beyond the mission hubs, a secondary web activates. From hobbyist setups in Puna backyards to automated scopes in Arizona, volunteers contribute light measurements and position data to communal platforms. A citizen observer might spot the initial brightness surge, yet experts now process these contributions live. Agencies release formal notices only after validation across tools, promoting restraint and careful assessment. Bold assertions demand robust backing. Pre-planned communication strategies for all outcomes emphasize openness sans hype. The community channel remains accessible, yet each phase aims to foster reliability, duplication, authentication, and provenance tracking, all to support a conclusion the global audience can trust. Within the RedWatch Operations Center, the evaluation framework anchors all discussions. It features 3 categories: cautious, risky, exceptional, for assessing the 3I/Atlas object as inputs arrive from the red planet. The cautious route applies if all oddities align with uncommon yet earthly comet traits, such as sequential gas releases from unstable zones, particles formed by exotic reactions, and minor thrusts within established physical bounds. Risky takes precedence if breakup remnants or particle swarms exceed danger limits, like over 10% mass reduction or erratic paths endangering satellite operations around Mars. Under such conditions, protective shutdowns and data sorting supersede research goals. The exceptional category remains distinct. It requires no fewer than 2 unrelated, highly probable irregularities, like coordinated signals aligning with tiny velocity boosts or emission patterns challenging all recognized chemistries, verified by distinct groups and apparatus. A solitary outlier, however bizarre, proves insufficient. The guideline is straightforward. Unified proof alone unlocks considerations of artificial origins. Staff fully grasp the implications. During this critical period, the framework transcends a mere diagram. It guides the forthcoming steps in space exploration. Updated guidelines now mandate that all interstellar transit data ascends a quick dissemination chain, reaching the public in hours rather than months. The era of restricted comet signals has ended. NASA, ESA, and JAXA have committed to duplicate storage systems where unedited and explained datasets stream to accessible platforms immediately after Earth receivers verify accuracy. Computerized processes highlight deviations. Quick access raw spectra enable immediate scrutiny, with calibration details embedded right beside the measurements. Mars mission crews now incorporate streamlined, rapid-fire data transmissions in crisis protocols for any fleeting occurrence, followed by comprehensive releases of detailed spectral and imaging files. Amateur involvement has evolved beyond mere hobby pursuits. Volunteer observer groups spanning from Pune to Patagonia feed photometry and positional data straight into validated processing streams. AI algorithms filter, verify, and prioritize these contributions for expert review, allowing an initial notification, perhaps from a home setup, to prompt formal investigation in mere moments. Regarding safeguards for planetary integrity, the Space Research Committee's newest proposal requires labeling irregularities on all biological indicators after close approaches, along with detailed tracking records for captured particles or organic materials. These updates aim to guide not only the upcoming trio of interstellar atlas objects, but also all subsequent envoys from outer realms, embedding accountability, reliability, and an international framework for handling mysteries. On October 3, 2025, when 3/Alas swept to within 0.19 astronomical units of Mars, all primary orbiters and surface explorers directed their instruments skyward. More than 40 hours of intensive observations streamed from MAVEN, Mars Express, and ExoMars TGO, documenting the entity's green luminescence, rhythmic intensifications, and dominant carbon dioxide composition, features unprecedented among documented comets. Although conventional explanations account for many aspects, the sequence of tiny velocity shifts and aligned pulsations defies clear explanation. The unprocessed datasets, now available for communal examination, form a permanent archive. Yet critical inquiries persist, including the emission's actual origin and any potential artificial influences. Undeniably, this brush with the unknown has spurred fresh guidelines for tracking extrasolar phenomena and established benchmarks for openness. Regardless of 3/2/Atlas's true essence, its close pass by Mars has reshaped our strategies and conversations around extraterrestrial arrivals.